So it's only fair we do a hypothesis test involving categorical data. And the most important hypothesis test involving categorical data is the chi-square test for independence. So let's start with an interesting example. Are eye color and gender independent? They're both categorical variables. We'll assume everybody's gender is male or female. And the eye colors we'll look at will be blue, brown, green, and hazel. And so basically what we will do is look at a bunch of students and count how many females had each eye color, how many males had each eye color. And this is the data that we have. And so what does it mean to say eye color and gender are independent? Well, you think back to Module 2, it means basically the chance that you would have blue eyes or brown eyes or green eyes or hazel eyes doesn't depend on your gender. So we should probably look at what fraction of these people in each gender had each eye color. So we can do that over here. So we could say the fraction of the females with blue eyes would be, we've got the total number of females here, it would be this fraction have blue, and we would divide by P7. But now when we copy that down to get it for males, we want the 7 to change to an 8, but when we copy this across, we don't want the P to change. So I'll $ that. Okay, so roughly 33% of the women have blue eyes. We need to widen the columns, I guess, there. And if I've done this right, that should add to 100%. Now, if I do that for the males here, those should also add to 100%. Okay, so now the question about the independence in our hypotheses are going to be as follows. The null hypothesis is that eye color and gender are independent. And the alternative hypothesis is eye color and gender are not independent. Okay, now what would be perfect independence? Well, perfect independence would be for females and males, would you see exactly the same fraction of them with blue eyes, brown eyes, green eyes, and hazel eyes. Of course, it's never going to be exactly the same, but the percentage with hazel eyes in men and women is pretty much the same. The percentage of blue eyes seems to differ, the brown eyes doesn't differ much, but the green and the blue eyes seem to differ a lot. The question is that a significant difference when you look over all the eye colors and all the genders involved in the problem? And that's what the chi-square test for independence can tell you, is the numbers that we see in this table, are they illustrating a significant deviation from independence, which would mean basically in each column the two numbers would be the same. So if you think about this, what we're going to have to do in the next video is figure out basically, we know the observed number in each of these cells of this thing called the contingency table. We need to figure out the expected number under independence and then see is there a significant difference between the observed number and the expected number. And there'll be a test statistic based on the observed number minus the expected number squared in each cell divided by the expected number. You add those all up, and that won't be a normal random variable. It won't be an F-test. It won't be a t-test. It's something called the chi-squared random variable. And like the t-random variable, it has a certain number of degrees of freedom, the number of rows minus 1 times the number of columns minus 1. And then basically, if you get a big value of this statistic, you'll reject the null. Because basically, if all these percentages in each column were the same, you would get a statistic of 0. So the bigger this statistic results in a rejection of the null hypothesis. So the next video will go about computing this test statistic, and then we'll get the results of the hypothesis, which will tell us are eye color and gender independent or not independent.